Hello student, welcome to your chemistry lab. Today I am discussing electrochemistry part 2, that is electrode potential, standard electrode potential and Nernst equation. It is important for JEE and NEET and also board. So read very carefully. So now watching the whiteboard. Electrode potential and standard electrode potential. If we connect two different electrons will flow from the electrode of higher negative electric charge density to the electrode with lower negative electric charge density. Electrode potential, a property closely related to the density of negative electric charge, is called electrode potential. Means potential difference between the metal and metal ion in which electrode is dipped is called electrode potential. Denote as a E, or the potential difference that the develop between the electrode and the electrolyte is called electrode potential. When a metal strip M is placed in contact with the solution of its own ion, that is Mn positive, and electrical potential difference is set up between the metal strip and the solution due to either of two tendencies. First, oxidation. M gives Mn positive plus N electron. Reduction, Mn positive plus N electron gives M. The electrical potential difference between the metal strip and the solution is known as half cell electrode potential, that is E. Single electrode potential cannot be measured experimentally. The potential difference between two single electrons can be measured by using potentiometer. The tendency of oxidation can be represented by oxidation potential, that is EOP, and the tendency of reduction can be represented by reduction potential, that is ERP. Oxidation potential of an element is same in magnitude but opposite in sign to its reduction potential, that is ERP equals to EOP. Therefore, by the convention, the electrode potential E are represented by their reduction potential, that is ERP. ERP values vary with concentration of the ions in the solution at a particular temperature. Standard electrode potential, that is E0, the reduction potential of the electrode at standard state condition, that is 1 molar concentration of the ion and 298 Kelvin and 1 atm pressure, is called the standard reduction potential, that is E0. The absolute value of E0 for any electrode cannot be determined because it is impossible to work with a single half cell. Hence the E0 values are determined with respect to standard hydrogen electrode, that is SHE, whose standard electrode potential E0 is taken to be 0 by convention. E0 is an intensive property like temperature or molar volume. This means E0 is the same for half cell reaction, whether represented as 2x plus 2 electron equals to x2 or x plus electron equals to half x. E0 values are not thermodynamic function and may not be added directly. However, they can be calculated from free energy, which is an extensive property. The value of electrode potential developed on an electrode potential upon first temperature of the system, concentration of ion in solution, chemical nature of metal or non-metal, number of electron transferred in the half cell reaction. It does not depend on electrode. Sign of electrode potential. When an electrode potential is coupled with normal or standard hydrogen electrode, depending on the nature of the charge acquired by it, potential of the electrode is decided as either positive or negative. Significance of the value and sign of the electrode potential. First point, the oxidized species of an electrode or half cell with large value of standard electrode reduction potential, that is E0 value, shows greater tendency to be reduced, and therefore it will act as a strong reducing agent under standard condition, that is reduction. Point 2. The reduced species of an electrode with small value of standard electrode potential has greater tendency to oxidize, and therefore it will act as a strong reducing agent under standard condition, that is oxidation. Electromotive force or EMF of the cell or cell voltage. The flow of current from one electrode to other electrode indicates that these electrodes are different potential. The potential difference between two electrodes is known as cell potential. It is maximum potential that a cell can generate and represented by E cell. Since the potential difference is the driving force for electron, it is also called electromotive force, that is EMF of the cell, and cell potential or the cell voltage. The driving force pushes the negatively charged electron away from the anode, that is negative electrode, and pull them towards the cathode, that is positive electrode. EMF of cell is equal to cell potential. When no current is being drawn from the cell potential depends on composition of electrode and concentration of the ion in the half cell and the temperature. In standard condition, cell potential is called standard cell potential, denoted by E0 cell. The SI unit of cell potential is the volt, and the potential of galvanic cell is defined as the positive quantity. Calculating the EMF of a cell. Mathematically, it may be expressed as E cell or EMF equals to ERP cathode minus ERP anode, means reduction potential of cathode minus reduction potential of anode. E0 cell means standard condition, that is EMF 0 equals to E0 RP cathode minus E0 RP anode. For cell reaction to occur, the E cell should be positive. This can happen only if ERP cathode greater than ERP anode, means reduction potential of cathode greater than reduction potential of anode. E0 cell must be positive for a spontaneous reaction. The rate of an electrolytic reaction is directly proportional to the EMF of the cell. The EMF of the cell depends on the intensity of the reaction in the cell. It measures free energy change for maximum convertible of heat into useful work. It causes flow of current from higher value of E0 electrode to lower value E0 electrode. Thermodynamic of cell. Electrical work, that is del G0, or spontaneous change, or relation between electromotive force of cell, that is E cell, and decrease in Gibbs free energy, that is minus del G of the cell reaction. The relationship between the volt SI unit of energy is joule and electrical charge, that is coulomb C, is given equals to 1 joule equals to 1 coulomb into 1 volt, where 1 coulomb is the amount of charge transferred when current of 1 ampere flows for 1 second. When 1 coulomb of charge moves between two electrodes, that differs in electrical potential by 1 volt. 1 joule of energy is released by the cell and can be used to be electrical work. Thus, quantitative measures of driving force of a chemical reaction are: A. The cell potential E, that is electrochemical quantity; the free energy change del G, that is thermochemical quantity. For a reversible cell, the electrical work derived from the cell is found to be maximum, that is W max. Del G represents the maximum amount of useful work that a constant pressure process can perform, that is del G equals to minus W max. For a spontaneous change del G less than 0 and work done by the system is negative, when a reaction occurs in voltaic cell, it does work, that is electrical work. Amount of electric charge carried by n mole of electron equals to n into F. Here 1 mole of electron carry 1 Faraday of electric charge. Here F equals to 1 Faraday. That is electrical work equals to quantity of electric charge into potential difference. So maximum work derived for reversible cell equals to quantity of charge into electromotive force. That is here quantity of charge equals to NF and electromotive force equals to E cell. That is W max equals to NF E cell. For a reversible cell, the decrease in free energy is equal to the electrical work done by the cell, that is minus del G equals to W max equals to NF E cell minus del G equals to NF E cell. If the reactant and product are in standard state, minus del G 0 equals to minus NF E0 cell. If E cell is positive, reaction occurs spontaneously in the forward direction. If E cell is negative, the reaction occurs spontaneously in the reverse direction. If a cell reaction is reversed, E cell changes sign, means sign of E cell will be changed. Relation between E0 cell and equilibrium constant, that is Keq. Del G0 is related to thermodynamic equilibrium constant by equation del G0 equals to minus RT ln K, and also del G0 equals to minus NF E0 cell. Therefore E0 cell equals to 2.303 RT by NF log K equilibrium. At 25 degree centigrade, means standard temperature, the value of 2.303 RT by F equals to 0.591 volt. Here R equals to 8.314, temperature to T equals to 298 Kelvin, and Faraday equals to 96,500. Total value equals to 0.0591 volt. Therefore E0 cell equals to 0.0591 by N log K equilibrium. Relation between standard potential of half cell containing a metal in different oxidation state. If two half cell having potential E01 and E02 are combined to give third half cell having a potential E03, then del G03 equals to del G01 plus del G02, putting the value of del G0 equals to minus NF E0. So minus N3 F E03 equals to minus N1 F E01 minus N2 F E02, and F are cancelled from both sides. Therefore N3 E03 equals to N1 E01 plus N2 E02. If the equal number of electrons are involved, then E03 equals to E01 plus E02. Nernst equation, the equation that is used to determine the equilibrium reduction potential of a half cell in electrochemical cell, is termed as a Nernst equation. For a reaction AABB equilibrium CC plus DD, reaction quotient Q equals to concentration of C to the power C, concentration of D to the power D by concentration of A to the power A and concentration of B to the power B, and del G equals to del G0 plus RT ln cube, and del G0 equals to minus NF E cell, and del G0 equals to minus NF E0 cell, putting the value of del G and del G0 in given equation, and minus NF E cell equals to minus NF E0 cell plus RT ln cube. So E cell equals to E0 cell minus RT NF by ln cube, and putting the value of R and T and F and calculating, E cell equals to E0 cell minus 0.0591 by N log cube, and E cell equals to E0 cell minus 0.0591 by N ln concentration of C to the power C, concentration of D to the power D by concentration of A to the power A, concentration of B to the power B. Here we are putting value of Q. Means Nernst equation equals to E cell equals to E0 cell minus 0.0591 by N log product by reactant. This is the final equation. Means we are remember this equation, E cell equals to E0 cell minus 0.0591 by N log product by reactants, means log concentration of product by concentration of reactant. Thus for the Daniell cell with cell reaction, Zn solid plus Cu2 positive aqueous gives Cu solid plus Zn2 positive aqueous. So Nernst equation equals to E cell equals to E0 cell minus 0.0591 by 2 log concentration of Zn2 positive by concentration of Cu2 positive. This equation can also be used to determine electrode potential of half cell. Here first half cell Zn slash Zn2 positive aqueous. Zn solid gives Zn2 positive plus 2 electrons, means E Zn2 positive equals to E0 Zn2 positives minus 0.0591 by 2 log concentration of Zn2 positive by 1. B Cu2 positive slash Cu2 positive aqueous plus 2 electron gives Cu solid. E Cu2 positive Cu equals to E0 Cu2 positive Cu minus 0.0591 by 2 log 1 by concentration of Cu2 positive. Adding equation 1 and equation 2, E Zn2 positive plus E Cu2 positive Cu equals to E0 Zn2 positive plus E0 Cu2 positive Cu minus 0.0591 by 2 log concentration of Zn2 positive by concentration of Cu2 positive. So total equation equals to E cell equals to E0 cell minus 0.0591 by 2 log concentration of Zn2 positive by concentration of Cu2 positive. Factor affecting electrode potential. Electrode potential is given by E cell equals to E0 cell minus 2.303 RT by NF log Q. Case 1. Electrode potential of oxidation half cell M/Mn positive aqueous with reaction M solid gives Mn positive aqueous plus N electron is E oxidation equals to E0 oxidation minus 2.303 RT by NF log concentration of Mn positive. EOX depends on concentration of ionic basis. If concentration of Mn positive increases, log Mn positive increases, hence EOX decrease, shown in figure. That is variation of EOX with log concentration of Mn positive. We can say electrode is reversible with respect to Mn positive, that is slope equals to 2.303 RT by NF, and when concentration of Mn positive equals to 1 mole, so log Mn positive equals to 0. Then OA equals to E0 oxidation. Point 2. Temperature. At constant concentration of Mn positive on increasing temperature 2.303 RT by NF increases, hence OX decreases. OX means O equals to O0x minus 2.303 RT by NF log Mn positive. Variation of OX with log Mn positive at temperature T1, T2 and T3 as shown in figure. Variation of OX with log concentration of Mn positive at different temperature, here T1 less than T2 less than T3. Case 2. Electrode potential of reduction half cell, that is Mn positive slash M with reaction Mn positive aqueous plus N electron gives M solid, is E reduction equals to E0 reduction minus 2.303 RT by NF log 1 by concentration of Mn positive equals to E0 reduction plus 2.303 RT by NF log concentration of Mn positive. E reduction depends on first Mn positive concentration of ionic pieces. If the concentration of Mn positive increases, E reduction increases. Electrode is reversible to Mn positive shown in figure, that is variation of E reduction with log concentration of Mn positive. Slope equals to 2.303 RT by NF, and when concentration of Mn positive equals to 1 molar, so E0 reduction equals to OA. Point 2. Temperature T. If the T increases, means temperature increases at constant concentration of Mn positive, E reduction increases. Variation of E reduction with log Mn positive at different temperatures shown in figure. Variation of E reduction with log concentration of Mn positive at different temperatures. Here T1 less than T2 less than T3. I think you are enjoying to watch my video. I hope you are understanding all the points. If are not clear, so comment me. I will be replied you. If are need to discuss any topics, please comment me. I will be discussing for you. And stay with your chemistry lab. So thank you everyone. Bye bye.